Hi, welcome back to our video 2. So this video is trying to let you understand why we use the enthalpy of formation and learning how to solve basic energy balance of the reaction. So now that we can balance the equation, let's look at how we calculate heat and energy balance. In earlier chapters where nothing changed chemically, finding enthalpy is very easy and simple. You just look up a value in the steam table and find the difference between the hash, which is delta hash. And because the substance didn't change, any arbitrary starting line used by the table will cancel out automatically. Look at the box on this slide. Hydrogen H2 and oxygen O2 gas enter and they will react and the liquid water is coming out. So hydrogen enter but never leave and water leave but never enter. Because the substance themselves are changing, standard table won't cancel out nicely. So to solve this, we must use a shared starting point called the enthalpy of formation. To give every substance a fair baseline, we create a standard reference state at 295.15 K, which is 25 degrees Celsius and 1 atm. We then declare that the enthalpy of any pure and stable element at this state is exactly 0. And the enthalpy of formation HF is simply the energy released or absorbed when 1 mole of a compound is built directly from its base elements at this standard state. So take a look at table A-25 on this slide. You will see that carbon dioxide CO2 has a value of negative 393,520 kilojoule per kilomole. That minus sign means that is an exothermic reaction and it gives off a lot of heat when it forms. This means that basic elements like carbon C, hydrogen H2, and nitrogen N2, and oxygen O2 have a starting value of 0. And then what do we do if a gas enters or leaves at a hot temperature that isn't than 298 K? We use a straightforward two-part formula, which is this long formula. And this means the total enthalpy of a substance is just is chemical bond energy HF from table A25. Plus or minus any extra sensible thermal energy, delta H, means that it gains or lost from changing temperature. So now let's put some effort into the practice question. Imagine the coal, pure carbon, enter a steady state burner at 298 K and burns completely with oxygen gas entering at 400 K. The resulting carbon dioxide gas leave the system at 500 K. So now let's find the net heat transfer rate per mole of coal. So our chemical equation is simple, C plus O2 equal to CO2. We write out our steady state energy balance. So after we got this given value, we first find out the energy rate balance on a molar basic, which is this equation. Since the WCB is equal to 0, so it can be neglected. And then we proceed, and we finally will get this equation, which is want to find the hash for the CO2, C, and O2. So we substitute the value for 298K and for 400K and also 500K. So after we got this all value, we can substitute into the equation 1 and get this answer. So this is the final answer we get, which is minus 388,235 kilojoule per kilomole. So the minus sign indicate the heat transfer from the control volume.